Hello, thank you for joining me for this virtual talk. My name is James Ferlez, and I'm a postdoc at the University of California, Irvine. Today I'm going to talk about our recent work, two-level lattice neural network architectures for the control of nonlinear systems. This is joint work with a PhD student, Zhao Sun, and my postdoc advisor, Yasser Shokri. ReLU neural networks are increasingly used as parameterized feedback controllers, where those parameters are learned from data rather than being designed analytically. For example, in deep reinforcement learning, instead of learning a general policy pi, we use a neural network and learn a policy by learning neuron weights and biases. Choosing the right values for these weights and biases is a problem that's been studied for a long time. This is called training. In deep RL, we can use the PPO algorithm on data from an MPC expert, for example. However, choosing the number and arrangement of neurons in the neural network, that is its architecture, has been less well studied. By contrast, this is a hyperparameter selection problem. In fact, the typical way of designing neural network architectures merely exploits what we know about training. It starts by guessing an architecture, training that architecture on some data, and then evaluating the resulting controller in closed loop. Then, depending on the performance of that closed loop controller, you may have to guess a new architecture, train, and evaluate, and so on and so forth. This design methodology comes with some serious drawbacks, one of which is computational cost, which is in part because it doesn't easily use a priori knowledge about the plant we're trying to control, such as from its physics. But second, and more importantly, this comes with no assurance of correctness. In particular, this methodology gives no guarantee that a particular architecture will eventually lead to a closed-loop controller that has some adequate performance. So it's this second point in particular that we're trying to address with this work. We want to generate ReLU architectures that come with some assurance about their performance in closed loop. So we start our problem statement with a continuous time nonlinear control system where the vector field is Lipschitz continuous, and we separate the Lipschitz constants into kx and ku. We further assume that there exists a Lipschitz continuous controller psi that operates on a compact subset of the state space and has a known bound on its Lipschitz constant k cont. In particular, this controller must satisfy some specification in the closed loop, where that satisfaction is up to delta robustness, a concept we will explain later. And for technical reasons, it should also make this compact set of states X positively invariant. Assuming the existence of such a controller may seem onerous, but it's important because it ensures the problem is well posed. In particular, we know the neural network controllers we're considering are necessarily continuous functions. However, we also know that there are nonlinear control problems which admit no continuous controllers. Hence, this assumption ensures that the overall problem is well posed. So the problem statement we're going to consider proceeds as follows. We assume we're given the various parameters we've described before. That's a robustness margin delta, the Lipschitz constants, the state and control sets, and a bound on the vector field of our ODE, shown on the screen. However, we emphasize that we do not assume we have detailed knowledge of the vector field F, nor the assumed to exist controller psi. We really just depend on these parameters listed on the screen right now. So given this information, the problem is to find a ReLU neural network architecture such that there exists a particular neural network of this architecture which, in closed loop, satisfies the same specification as the assumed to exist controller psi. And we just make a small note here. For technical completeness, this notion of delta robustness will depend also on these parameters we listed above. Our approach to this problem can be divided into three steps. The first step we can summarize as approximate controllers also satisfy the specification. So in our problem assumptions, we have assumed the existence of a Lipschitz continuous controller that satisfies the specifications. However, we know that no neural network architecture can realize that controller exactly. Thus, we have to show that even approximate controllers can satisfy the specification. In particular, we have to find an approximation accuracy mu, such that even mu approximate controllers also satisfy the specification. And it's important to note that controller errors in closed loop can accumulate, and this is why we need the robust specification on psi. Another way of saying this is that when psi satisfies the specification robustly, instantaneous controller errors of no more than mu will also meet the specification. In the second step, which we can summarize as a Lipschitz continuous function can be approximated by a continuous piecewise affine function, we want to show that we can obtain a CPWA controller that meets the accuracy we specified in step 1. And hence, of course, this will imply the existence of a CPWA controller that satisfies the specification. In particular, our methodology must be independent of the particular psi, which we recall we don't know the details of. And so it's got to depend only on the parameters k cont, mu, and x. And for reasons in step 3, the number of linear regions in the CPWA must also depend on the same parameters. The method that we're going to use to achieve this is to put down a regular grid of non-overlapping hypercube patches and interpolate between constant functions on these patches in a linear way. Finally, in step 3, which we can describe as the architecture design step, we can simply use prior work where we showed that a CPWA can be represented by a TLL architecture as long as you have knowledge of the number of linear regions in the CPWA. And so combining 1, 2, and this theorem from our prior work, we end up with a neural network architecture that solves the main problem. So we'll start with step 1. The most important aspect of this step is the nature of the specification for the assumed to exist controller psi. There are plenty of other calculations, but they're more or less routine, and you can look to our paper for more details. So recall, we assumed the existence of this Lipschitz continuous controller psi, but we know that no neural network architecture can represent it exactly in general. And so the question here is, how can we write a well-posed specification for psi in the closed loop? That is, one for which we can eventually satisfy the same specification within neural network architecture. So our approach to this is to start by considering a tau-sampled transition system embedding of the original nonlinear control system. This is a concept that's well studied. The states in this transition system will just be the states of the compact subset X, and a transition between states will be possible if and only if the closed-loop controller psi takes one state to the other in tau seconds. Now, moving to a transition system, we have a natural notion of specification, and that's via simulation relation. And so in particular, we can say that our tau-sampled embedding satisfies a specification if it is simulated by a transition system description of the particular specification we're interested in. However, crucially, we know that our neural network will not be able to represent psi exactly. So this simulation relation alone won't be enough to account for errors in the closed-loop controller. To illustrate this, suppose that X is simulated by P in the specification. X transitions to X prime under the controller psi, and X prime is simulated by P prime in the specification. However, if we apply instead our neural network controller, we know that we'll end up in a state other than X prime. And the problem with the simulation relation described above is that this particular state may not be simulated by a target of P. Our solution to this problem is to define our specification in terms of an abstract disturbance simulation relation, a new concept that generalizes some existing notions in the literature, notably robust bisimulation, and especially disturbance bisimulation. However, abstract disturbance simulation generalizes these notions away from the particular systems on which they were defined. Delta abstract disturbance simulation is most simply defined on transition systems with identical metric state spaces, but it has two important properties. One, related states are delta close, and two, most importantly for our purposes, delta perturbations of the target states must also be simulated. So in mathematical notation, if X is simulated by P, and X transitions to X prime, and X prime is simulated by P prime, then for any X double prime that's delta close to X prime, there should exist some P double prime, such that P double prime simulates X double prime. This solves the problem of using approximate controllers in closed loop. So suppose X is simulated by P, and X transitions to X prime under the closed loop controller psi. Now if we have instead an abstract disturbance simulation relation with parameter delta, then any state that is delta close to x prime must also be simulated by the specification. So in particular, if we can choose our neural network controller to get within delta of the target state obtained by using the original controller psi, then we're guaranteed that that state will be simulated by some state in the specification. And so you note that disturbance simulation implies simulation for the disturbed or perturbed system. So now we'll talk about step 2. Recall from step 1, we know an approximation accuracy that's required of an approximate controller so that it meets the specification. And in step 2, our task will be to find a CPWA that meets this approximation accuracy. As mentioned before, our method will be to put down a regular non-overlapping grid of hypercube patches and linearly interpolate between constant functions on these patches. Importantly though, this scheme can't depend on the particular value of the function psi on those patches. Recall psi is unknown except for its Lipschitz constant k-cont. And for reasons related to the architecture design, the total number of linear regions in the CPWA has to likewise depend only on the problem parameters rather than the particularities of the function psi. To illustrate this procedure, we will demonstrate it on a particular psi. So in the figure on the screen now, you can see what constant functions look like on a regular non-overlapping grid of hypercube patches. And in particular, the constant values on these patches are taken as values of psi within the patch. This leaves the problem of interpolating between these constant functions in a continuous and linear fashion. And so in this paper, we show that this can be done consistently. And in particular, linear interpolation between full dimension faces of these hypercube patches can be done more or less directly. In this example, the full dimensional faces of the hypercubes are line segments. And so these interpolations are shown with the red linear functions. However, this still leaves some gaps between the lower dimensional faces, but we show that these can be interpolated linearly by extending the red linear functions in a consistent way. And so in this particular illustration, these interpolations are shown with the green faces. So step 3 is the architecture design. From step 1 and step 2, we know we have an approximate CPWA controller that meets the spec. And moreover, it has some total number of linear regions that depends only on the problem parameters. And so if we set n bar to be the number of linear regions we use, then we can simply appeal to prior work, where we can design a neural network architecture purely based on the number of linear regions we want to have in it. And that's the two-level lattice architecture, and this is a theorem from our HSCC paper from earlier this year. So just to wrap up, I'm going to describe the main theorem in the paper. So there's a lot to take in here, and there are a lot of details, so you'll probably have to look some of these up yourself, but I'll try to emphasize the important points. So first, this inequality defines the approximation accuracy mu that is required of an approximate controller so that it satisfies the specification. And you'll note here that this inequality depends only on the problem parameters, including the robustness margin, delta. So once this mu is chosen, we can likewise define a sample interval for our tau embedding that is defined in terms of only mu and the problem parameters. Then furthermore, we can set the size of the hypercube patches based on mu and the problem parameters. Given these definitions then, the primary assumption of the theorem is that there exists a controller psi that robustly satisfies the spec for the particular choice of the sample interval defined above. This specification is, as we mentioned before, delta abstract simulation. So assuming the existence of such a controller psi, the conclusion of the theorem is then that if you take a TLL architecture with number of linear regions n, at least the size shown on the screen, then that TLL architecture will have the property that there are parameter values for which the resulting network satisfies the specification, albeit not robustly. And in particular, this solves the problem that we posed. With that, I'll be happy to take any questions. Thank you for your attention.